In this video, I'll explain the Euclidean algorithm for the greatest common divisor of two numbers. If you take two numbers, let's say 24 and 36, the greatest common divisor is the greatest natural number which divides both of them without a remainder. So in this case, you can see that the greatest common divisor of 24 and 36, in this case, it's easy to see it is 12. So how did we know this? So the first method, say we enumerate all the divisors of 24, all the divisors of 36. Now the common divisors are 1, which appears in both, 2, 3, 4, 6 also, not 8, not 9, we have 12, and that's all. And the greatest common divisor is clear, it's 12. Another way to do it is to find the prime factorizations of 24 and 36. So I say 24, I can divide it by 2, I get 12. By 2, I get 6. By 2, I get 3. And by 3, I get 1. So I write 24 is equal to 2 to the power 3 times 3. And for 36, I do the same thing. I realize I can divide by 2 to get 18, and by 2 I get 9, and then I divide by 3 to get 3, and by 3 to get 1, and I write here 36 is 2 to the power 2 times 3 to the power 2. And now the greatest common divisor is given by, like, the prime factors which appear in both the factorizations are 2 and 3. So I have here 2 to the power. I take the smallest power or 2 of 2 which appears. So it's this one. So I have 2 to the power 2. And for 3, I take it to the least power which appears in those factorizations. So it's the 1 here. 3 to the power 1. And this is, of course, 12. The Euclidean algorithm is a third algorithm to compute the greatest common divisor. So the first question, I have already 2 ways to compute the greatest common divisor. Why should I look for a third one? There are many reasons, in fact. One of them is that when you apply the Euclidean algorithm, you have something which is called the Bézout identity. And this is useful for computing modular multiplicative inverses of numbers. We will talk about this later in later videos, and this will be essential in the application of number theory to cryptography. We'll talk about all this later. Another reason why we like the Euclidean algorithm is efficiency. And this is a very, very good reason why we should like this algorithm, rather than the 2 algorithms I described before. So what do we mean by efficiency? Well, for small numbers, we don't talk about efficiency. But for very large numbers, like for example, each time your web browser wants to have a secure connection to some server, the usual protocols use numbers of the order of 10 to the power 600. So numbers, if you want to write them down, like in their decimal representation, you need let's say 10 lines or something like this. So a huge number. If you are given 2 numbers A and B of this size, and you want to compute the greatest common divisor of those, with Euclid's algorithm, the number of operations, the number of steps that you have to do to compute the answer will be comparable to the size of these numbers, which is around 600. Like 600 steps, comparable to 600, perhaps the square of that, or a constant times the square of that, or something like this, like a few thousand steps, which is just nothing for your computer. Your computer can do it like in milliseconds, perhaps even microseconds. But if your computer wants to compute the greatest common divisor using one of the above algorithms, so he will have to make around 10 to the 600 steps, which is a huge number, which no computer can do. And the reason being is that there is no efficient algorithm to find the prime divisors of a given large number. Now, if you have a quantum computer which works well, you have an algorithm called the Shor's algorithm. But on a classical computer, there is no such thing. And in fact, the security of the algorithms used in cryptography today Many of them rely on the fact that the prime factorization is a hard computational problem. However, with Euclid's algorithm, to calculate the greatest common divisor or to calculate the modular multiplicative inverse, you don't need to find the prime factors. That's why it's interesting. So how does it work? It all starts with the following remark. Like given two numbers a and b. Suppose one should be larger than the other. Suppose a is greater than b. Now if you divide a by b, you write a equals some quotient times b plus some remainder. Then any number which divides both b and the remainder must divide a. It's clear. If it divides b, so it divides q times b, and if it's a divisor of r as well, then it should be a divisor of the sum q times b plus r, which is a. So I write here if x divides b and r, it divides a. Now, if you take an x which divides a and b, so in this case, for sure it should divide r, because r equals a minus q times b. So I write here if x divides a and b, it divides r. So from this we conclude that the set of divisors of both a and b is the same as the set of divisors of both b and r. And then the greatest of the first set is equal to the greatest of the second set, because it's just the same set. All this to say, like the greatest common divisor of a and b is the same of that the greatest common divisor of b and r. Because as we said, the divisors of a and b are the same as the divisors of b and r. So the greatest of those is the same as the greatest of those. Now why is this interesting? Because instead of computing the greatest common divisor of a and b, compute the greatest common divisor of b and r. And now you have to deal with two numbers smaller than the numbers before. Instead of a, you have a smaller number which is b, and instead of b, you have a smaller number which is r. But now how do you compute the greatest common divisor of b and r? Perhaps those are still big numbers. So you repeat just the same arguments. You divide b by r and you take the rest r prime. And instead of GCD of b and r, compute GCD of r and r prime. And continue this until you finish with two numbers where the greatest common divisor is obvious. In order to describe this algorithm more precisely, so let's choose some change a little bit the notation. So suppose I want to compute the greatest common divisor of two numbers. I call them a0 and a1. And without loss of generality, let's suppose a0 is greater than a1. What I do first is a first division. Like I write down a0 is some quotient q0 times a1 plus some remainder. I'll call it a2. Now I'm interested in the greatest common divisor of a0 and a1, but I just said that this is the same thing as the greatest common divisor of a1 and a2. And I divide then a1 by a2. So I get a1 is some quotient q1 times a2 plus some remainder. I call it a3. And now I have that the greatest common divisor of a2 and a3 is the same as the greatest common divisor of a1 and a2, which in turn is the same as the greatest common divisor of a0 and a1. And I continue this way. So I divide a2 by a3. a2 equals q2 times a3 plus a4. And so on and so forth. Now if I continue, what will happen? In fact, a2 is strictly smaller than a1. Why? Because a2 is the remainder by a division in which the divisor was a1. Remainder is always smaller strictly than the divisor. And for the same reason, a3 is smaller strictly than a2. And a4 is strictly smaller than a3. So what I get here is a sequence of natural numbers which is strictly decreasing, which should be positive because those are remainders. So at some point I'll get to 0. And at 0 the algorithm stops, because in fact I cannot divide by 0. So let's say we continue and we get something like an is equal to qn times an plus 1 plus an plus 2, and then I get 0. So an plus 1 is qn plus 1 times an plus 2 plus 0. If I continue the division, I have to get here, because I just said that the sequence of the ans is strictly decreasing. So it has to stop. But as long as the ans are not 0 I can continue. So if it stops, I must have a 0. So this is an a n plus 2. I write it as q. Now I say that the last non-zero remainder, which is this one, is the greatest common divisor of the numbers a0 and I1, the numbers I started with. The last non-zero remainder. Why is this true? Well, first of all, when I divided an plus 1 by an plus 2, the remainder was 0. So, in fact, an plus 2 divides an plus 1. And what's the greatest common divisor of these two? Greatest common divisor of an plus 1 and an plus 2 is just an plus 2, because an plus 2 divides an plus 1. So I can say that an plus 2 is the greatest common divisor of an plus 1 and an plus 2. But this in turn, as we remarked, is the greatest common divisor of an and an plus 1. Because if a number divides these two, then it divides these two, by the same remark I've given above. And by induction, with the same argument, this is the same as the greatest common divisor of an minus 1 and an, which is the same as the greatest common divisor of an minus 2 and an minus 1. And by induction, I go back to the top. So an plus 2 is the same as the greatest common divisor of a1 and a2, which are the two numbers we started with. So that's all. This is the Euclidean algorithm. Now we have a few things to say. First of all, why is it efficient? Like, why all these steps are few steps? And two, we want an example. So let's start with an example, with an easy example. So take like the example of the beginning, where the first number of 24 and the second number is 36. So I want the greatest common divisor of those two. What I said is that I divide the biggest one by the smaller one. So 36 is 1 times 24 plus 12. The greatest common divisor of 36 and 24 is the same as that of 24 and 12. So I divide 24 by 12. I get 24 is 2 times 12 plus 0. And now I got a remainder which is 0. And the greatest common divisor is the last remainder which is not 0, which is 12. This is what we already checked. So let's do another example. So say I want to compute the greatest common divisor of 150 and let's say 112. And now I say 150 is 1 times 112 plus 38. Now I take 112 and 38. 112 is 2 times 38 plus 36. Now I take 38 with 36. 38 is 1 times 36 plus 2. Now it becomes very easy to see. I take 36 and 2. 36 is 18 times 2 plus 0. So I got to 0, and the last non-zero remainder is just 2. So the greatest common divisor is 2. So the idea, I repeat, the greatest common divisor which interests me is that of 150 and 112, but this turns out to be that the same as the greatest common divisor of 112 and 38. And now the greatest common divisor of 112 and 38 is the same as that of 38 and 36. And each time I'm getting smaller numbers, so it's easier to guess, but I can go to the end. That of 38 and 36, when I make the division, is the same as that of 36 and 2. And now 36 is divisible by 2. So the greatest common divisor is 2. So that's the idea behind the Euclid's algorithm, which was known since Euclid, like 400 years ago. So to make sure that you understood it properly, like just try it with some two random numbers you choose, like something like 1036 and 312. Just try to do it. Or even you can take much larger numbers. It's efficient, so it will work, like this number with this number, let's say. You can do it by hand. You don't need a calculator to do that. Just some patience. But if you want to apply the other method of factorization, factoring this number could be just complicated. You have to make many steps, try many numbers smaller than this one to find the prime factors of this.